Can everyone hear me? Yeah. And so this is joint work with Shaked Flur, Will Deacon, John French, Susmit Sarkar, and Peter Sewell. And Will Deacon has been working on this at ARM. Right. What's the semantics of concurrent power and ARM machine code programs? We've been working on the same question for the past 10 years, and the answer kept changing. This line of work started off by trying to formalize the architecture text on the concurrency behavior. And when it turned out that that was too imprecise, we continued by inventing new models in collaboration with the architects. And these models kept getting more and more complicated with each iteration as they were covering more aspects of the concurrency behavior and covering the sort of describing the behavior more accurately. Until now, where for the first time things are getting simpler again in the case of ARM. And in particular, the product of those years of work were our previous flowing and pop models from POPL'18 and 17 that ended up being quite complicated because ARM had the intention to make the architecture as weak as possible. And so as a result of the complexity of this model, and at the point of now better knowing what future hardware would look like, decided they wanted a simpler concurrency model. And this is what this talk is about. There's now a much simplified concurrency architecture, and for the first time, ARM has an official formal concurrency model as part of the architecture documentation. And so I'd like to talk about the simplifications that ARMv8 brings, the official axiomatic concurrency model, a simplified operational concurrency model, hand proof of equivalence between the two, and a testing and debugging tool built on top of the operational model. And I'll start off by talking about the simplifications in the behavior the revised architecture brings. The biggest change here is multicopy-atomicity. And this means that when a write propagates from one thread to another, it has to propagate to all other threads at the same time, which is a big conceptual simplification, and means, for instance, that in this litmus example here, where you don't have to look at all the details, but what this test was showing previously is that, so in the previous architecture, this write of x equals 1 from thread 0 was able to propagate to thread 1 without propagating to thread 2 at the same time. And this is now forbidden, because when this write propagates here to thread 1, it has to propagate to thread 2 as well immediately. So this is now forbidden. Another big change is in the definition of dependencies, where the architecture was previously introducing a notion of true and false dependencies using text like the one I'm quoting here, and requiring processes to only preserve true dependencies. And this has been changed now. The architecture doesn't make this distinction anymore. Right. Another change is concerning so-called vanishing writes or write subsumption, where if you look at this litmus test, only at the right-hand side actually, you have a read of y and a data-dependent write of x equals 1, and the following write of x equals 2 that is not data-dependent. Now previously, this write of x equals 2 was allowed to go ahead into memory early before this write of x equals 1, and thereby sort of subsuming it. This has now been strengthened to say that the write of x equals 2 must wait for this write of x equals 1. So the data dependency going into this write is strengthened. And there's one other change that I won't talk about now. There previously was a concept of symbolic forwarding, and the corresponding behavior is now forbidden. But I won't talk about this now. But what's important is that all of those changes apply back to ARMv8.0. They've been sort of backported because none of the existing hardware exploited the weakness of the previous specification. Right. And now turning to the models. So there's now this official axiomatic concurrency model by ARM, written by Will Deacon. And this is what it looks like. You don't have to read the details, but sort of compared to other axiomatic concurrency models, this is quite simple. It's written in the herd language, and so it defines a set of relations over memory events, and then a set of, in this case, 3 axioms involving these relations that all legal executions have to satisfy, usually requiring the acyclicity of certain relations. And in particular, this model defines the relations dependency ordered before, atomic ordered before and barrier ordered before that describe the thread internal ordering that all processes have to preserve. And the main axiom, which requires the acyclicity of this relation ob, basically requires that the interaction across threads described by the observed by relation, which contains reads from and some other relations, has to be compatible with the ordering preserved by the threads. And there's two other axioms. One is a standard per thread coherence axiom, or SC per location axiom. And the last one, an axiom concerning the exclusive, the guarantees given by load and store exclusive pairs. And to see how this works for an example, if we take this previous right subsumption litmus test, this particular behavior is forbidden by the axiomatic model because we have a cycle of the shape address followed by read from external. So read from external is read from between two different threads. Then data followed by coherence internal and read from external again, where each of these edges highlighted here are a member of this ob relation individually, and the main axiom requires that this relation be acyclic. So this is how the axiomatic model forbids this particular execution. Right. So there's this axiomatic model as part of the architecture documentation. Why have two models? The operational model has been the basis for our discussion with the architects, and they were sort of co-designed in collaboration between ARM and us. But apart from that, these two styles of models seem to have different advantages and disadvantages. The axiomatic model is nice in that it's more abstract because it works at the abstraction level of pure memory events, and it's very good at directly giving you properties of full executions. The operational model, on the other hand, is good because it gives you a more concrete hardware intuition, and so it gives you more confidence in the model, which comes at the expense of additional complexity. But part of this complexity is also due to the fact that the operational model handles more features than the axiomatic one does. It supports mixed-size concurrency, is integrated with a fairly extensive ISA model, and talks about the semantics of actual ELF binaries rather than only litmus tests. And now where this axiomatic model gives you these global properties of full executions, the operational model computes incrementally. So it incrementally builds legal executions and offers you induction on traces. Right. What does this operational model look like? Well, the starting point for this is the previous flowing model from POPL'18, 17, which is a transition system. So you have states and transitions between them, between the two, and it consists of two components: the thread subsystem and the storage subsystem, where the thread subsystem manages the out-of-order and speculative execution happening within the threads by maintaining this tree of in-flight instructions and enumerating their transitions. And it communicates with the storage subsystem that manages the propagation of writes across threads and replying to read requests. But now in this multi-copy-atomic setting, propagating writes is simple. And so the new model that we call flat, the new operational model, replaces this storage subsystem by a simple flat memory, basically an array or a mapping from address to values, because all of the remaining relaxed behavior can be explained in terms of the parallel composition of the threads. And we had to slightly adapt the thread subsystem to make this true. The details of this model are too much to talk about here, but to give you an idea of this model, these are the transition names we have. So all instructions first fetch and decode, and then they might do a series of register reads and writes and internal computation before eventually they finish. And then loads, stores, and barriers have special additional transitions, namely loads. When they've done enough register reads and to determine their address, they are set to initiate. And once initiated, the different reads belonging to a load, and this might be multiple in the mixed size case, can be satisfied either by thread internal forwarding or in memory. Once all of them are satisfied, the load can complete and eventually finish. And stores have similar transitions. Barriers have the additional commit barrier transition. Right, now to give you an idea of how this model looks like. I'll show you how it behaves for a small message passing test. So what this view gives you is basically the unfolded instruction tree per thread. This is the tree for thread 0, where we have a write of x equals 1, a strong barrier, and a write of y equals 1. And on thread 2, now I have to turn on the transitions. Right, on thread 1, we have a read of 0, followed by a conditional branch, depending on this read of, it was a read of y. We have a conditional branch depending on this read of y and read of x. So this read of x is control dependent on the read of y. And now what this tests for is whether we can here read y equals 1 from thread 0, but at the same time read x equals 0, the old value from the initial state. And the operational model explains this because this control dependency is weak, and we can speculatively execute this read of x here. So we do the read of x equals 0, read from the initial state. We do the write of x, do the barrier, do the write of y, and do the read of y. And now, well, you have to squint a bit, but you can see a cycle of the barrier, the reads from, the conditional branch, and from reads. But this is a cycle that the axiomatic model does not forbid. Now, how does this operational model relate to the axiomatic model? Well, we've hand-proved it equivalent to the axiomatic model, and the experimental data we have for our test suite of 6,500 systematically generated litmus tests agrees with this hand-proof. This hand-proof has to show two things. Given an execution allowed by the operational model, we have to show that the axiomatic model allows it as well, and the other way around. But because they have different notions of execution, this means showing that if we have a valid operational model trace inducing a particular axiomatic model candidate execution, then this same candidate execution is accepted by the axiomatic model, and the other way around. And a basic problem we face in this proof is that there's a mismatch between the events the two models talk about. Because where the axiomatic model has a single event per instruction, the operational model has multiple transitions for each load, store, and barrier. And so the idea underlying the proof is that there's a correspondence between particular operational model transitions and axiomatic model events, namely the satisfy read transitions, the two variants for loads, the propagate write transition for stores, and the commit barrier transition for barriers. And now in the first direction of the proof, so we have to show given an execution allowed by the operational model, this execution is allowed by the axiomatic model, means we have to show that these three axioms hold for this execution. The interesting part is in showing that the main axiom holds, that this relation ob is acyclic. And the idea here is that if we use this previous event transition correspondence, then we can interpret each of these edges from ob as an edge between transitions. And so if we can show that each of these edges individually is contained inside the operational model trace, which is linear by construction, viewed as a relation, then this proves the acyclicity of ob. And so to give an idea for this, if you take this edge address followed by program order to a write, this is an edge from a read to a write. And so under this correspondence, it's an edge from a read satisfy to a write propagate transition. And it pops up well, this is a program fragment that illustrates this, where you have, so it's a dependency from A to C, where C is a write, A is a read that feeds into the address of a memory access, read or write, program order before C. And now we can explain that in the operational model, this is in fact an edge in the trace, because for C to propagate into memory, it has to meet certain coherence requirements, which includes that all program order previous memory accesses, and in particular B, have to have their address determined, which implies that A is satisfied. And we can proceed in a similar way for the other edges here. which gives us the first direction of this proof. The second direction of the proof is more difficult, going from axiomatic to operational model, because we now have to show that given only an axiomatic model candidate execution, we can construct a valid operational model trace. But the operational model is quite big, has a lot of machinery, so constructing a legal trace is difficult. And what we do here is we introduce an intermediate model called flat axiomatic, which tries to capture the behavior of the operational model as closely as possible, but in this axiomatic language, so that this part of the proof, going from flat axiomatic to operational, is only about bridging between these two languages. And the interesting part is in showing this, the relation between these two axiomatic models, and this is mostly by relational reasoning. Right. Apart from this proof, we've been working on a testing and debugging tool built on top of the operational model called ARMv7, previously PPCmem, which has a new web interface that you already saw when I was showing the operational model for this message passing test. So it has this interactive mode I was using, but it also has a pseudo-random mode for testing and debugging concurrent algorithms, and an exhaustive mode for sort of model checking small concurrent programs, for which we've done some performance optimizations. I'll give you an idea of how this looks like. We've used this in the paper to check the correctness of a loop-unrolled Linux kernel spinlock implementation that contained a previously, so we checked both a version that contained a previously known bug and a fixed version. And so this is what it looks like. We've loaded up this test inside the model. Here it's written up as a litmus test for better readability, but we can load it as a proper ELF binary. And what you can see is that it uses proper instructions. It has, well, you can't see that it uses mixed size, but so it's a good test for the operational model because it has needs some features the axiomatic model doesn't have. And at the end, we specify a condition that corresponds to an invariant this spinlock implementation wants to preserve. And what we do in the paper is we use this pseudo-random exploration to see if we can find bugs in the version that contained this previously known bug. So what we can do is we run it randomly like this. And now it finds, this is just reporting that it found, this might be too small for you to read. This is reporting just that it reached the loop limit, so we run it again. Right, and now oh, this is also loop limit. Right. So now this is finding an execution where this invariant at the end of the test was invalidated. And now, if we were debugging, we could click this link and now sort of step through to hopefully figure out what's going wrong in this execution to debug this program. And in a similar way, we've run this on a fixed version. We've run this exhaustive mode for a loop-unrolled fixed version to sort of model check the absence of this bug. Right. Now I'll conclude by mentioning some of the caveats to this. Firstly, the features covered by the axiomatic and the operational model are not the same. The axiomatic model is not mixed size yet, and it is not integrated with this extensive ISA model. The operational model, on the other hand, does not handle the weaker form of load acquires yet that were introduced in ARMv8.3. And then the operational model, for some sort of pathological tests, it might deadlock for load and store exclusives, which is mostly a problem for interactive use, so you have to sort of backtrack when you reach this deadlock state. And finally, the proof, it's not formalized yet, it's only a hand proof. It covers finite executions only and addresses only the intersection of the features covered by both models. Right, to conclude, there's a much simplified ARMv8 concurrency architecture, partly due to this previous modeling efforts. We have a matching operational and the official axiomatic concurrency model, hand-proved equivalent, and a testing and debugging tool, ARMv7 built on top of the operational model with improved user interface and performance. And what's coming up next for future work is firstly integrating the operational model with the full ARMv8A ISO model and making this public, and some other ones you can read here. Thank you.
So I'll start off by online questions. They seem quick. One question is, ARMv8 sounds like a pretty strong model. What is the remaining difference with TSO?
Well, I guess the biggest difference is that load buffering is allowed, which, as I understand it, is not in TSO. So there are quite a few behaviors resulting from this that are not allowed under TSO, but allowed in ARMv8.
Okay.
Hi there. So one thing that I thought was quite interesting, although you ran very quickly past it, was that you said that in the operational model you are looking at speculative evaluation.
Sorry?
Speculative evaluation.
Yeah.
Which is very much in the headlines at the moment. So
right.
I was wondering if you could expand a bit on that.
Yeah. Well, so the model. Right. The model illustrates this speculative execution. You can see it in the operational model, but it seems that the operational model is not working at the same abstraction level where you could make this exploit visible in the model, because the model doesn't talk about caches explicitly and cache timing and these things that you would need to talk about this this exploit. But you can see this speculative execution happening to the degree that that it's necessary to explain the concurrency behavior.
So in the model that you've got, because you're not modeling timing attacks and you're not modeling caching behavior, does that mean that there is actually no information flow going from an aborted speculation into regular code?
Yeah, yes, discarded branch or sort of speculative execution along a branch that will eventually be discarded is sort of pure with respect to the model state, whereas it wouldn't be if we were modeling these timing things.
Good.
Sorry, I missed the beginning of your question because the highest voted one is, maybe I'm repeating the question one more time. Is your operational semantics speculative on branches? Was that
Sorry, is it?
Your operational semantics, is it speculative on branches?
Yes.
Was that the same thing that you just discussed?
Guess similar point, yes.
Okay, yes. Any more questions from the audience here? I have one more. Does ARMv8 have a strictly stronger model than previous ARM versions?
I'm not completely sure whether this is true for all the cases of ARMv7. I think it is, but there's lots of details. I might be missing out on something. So the big change is multicopy-atomicity, and this is something where ARMv8 is strictly stronger.
Okay. And the last question is multi-copy semantics also applicable to non-atomic shared memory?
I can't answer that. I don't know.
Okay. Any more questions? You don't have a question? Okay. Thank you very much.